The subset of a vector space is a subspace, and here we define some subset we call capital W, to be a subset of the vector space V. And we say that W is a subspace if two things hold. The two main criteria I should note for linear algebra, that is, that the subspace vectors hold for vector addition and scalar multiplication. So hence, instead of showing 10 axioms for a vector space, here for a subspace we only show 2. The 2 that we show, if you go back to the 10 axioms for the vector space, is the first 2 headers, A1 and M1. A1 is the closure property for addition, for vector addition. This will be, for this theorem here, if W is a non-empty subset, that means that the space or the set W has to have something in it other than the empty set. Then W is said to be a subspace of V. V is here, some vector space, if and only if the following 2 conditions hold. 1 and 2. 1 is A1 from the vector space axiom. And number 2 is M1. This second one is the closure with respect to scalar multiplication. Just show those 2. And that's sufficient for a subspace. So the examples here that follows. Determine which of the following are subspaces here of R3. So we say let U be, why don't you do that? Be the vector that, let's say it looks like this, A, comma, 0, comma, 0. And V looks like B, comma, 0, comma, 0. And let's say K be some real number, a scalar. So first, we want to show that if U and V are in this subspace, we call it W, this subspace here that is of the form where it's a 3-tuple, the first component is some number, and the second and third component of the vector are 0. Right? So this is what W is defined as. Then U plus V is equal to here A plus B, comma, 0, comma, 0. That's still of that form. Secondly, if U is in W and K a scalar, then K times U is equal to KA, comma, 0, comma, 0. It is also of that form. So we conclude here that W is a subspace of R3. Again, we only show 2. Secondly, all vectors of the form here, A11, and we'll just say that this is some element of this subset. If W is not a subspace, then it's indeed a subset. W is a subset of V. So W can be a subset of V, but W may not necessarily be a subspace. So here, W can be within something, but the strict definition for the subspace, we have to adhere to these 2 properties. So here, let U be A1, 1, and V equals B1, 1, and let K be some real number. So then, U plus V is equal to A plus B, comma 2, comma 2. Uh-oh, this is not in W, because W is set to be of this form. Right? So that one fails, and then likewise the second one fails. KU, which is KA, comma, K, comma, K. This is not in W, so we conclude that W is not closed with respect to vector addition, and W is not closed to scalar multiplication. So W is not a subspace. Number 3, all the vectors of the form, some vector ABC, where the middle component is equal to the sum of the first and the last component plus a 1. So here we say that this represents W. Let U equal to A, comma B, comma C, and V, D, comma E, comma F. We get the setup for U as given that B is equal to A plus C plus 1. So here, where E is equal to D plus F plus 1. So if U and V are in W, then let's look at the sum of U plus V. Then U plus V is, if you don't mind, just go ahead and just add them here. This is A plus D, B plus E, C plus F, where let's see what happens to the sum of B plus E. That's equal to A plus C plus 1 plus D plus F plus 1. That equals to A plus C plus D plus F plus 2. Right. Should be plus 1. What about the second one? K times U is KA, comma, KB, comma, KC, where KB is equal to KA plus KC plus, here this is 1. Just based on that. Let's see, where is B? B is here. Yes. that slipped for a little while. James, you're back in business, man. Can you catch? Well, can I throw? That's what I'm talking about. Thank you, James. It's going to be a good day today, class. Well, if that was indeed Ka plus Kc plus 1, then that would have helped us in terms of trying to form a subspace, but it still would not be a subspace because part 1 failed as well. So, but they both failed. So here W is not a subspace. Number 4, determine which of the following are subspaces. Here, capital M, N, N is the space of all n by n matrices. So here, where it says number 4, the set of all diagonal n by n matrices, I cannot use a 2 by 2 or a 3 by 3 to represent my explanation. I have to use an n by n matrix. Well, here we need at least 2 of them. So we say let A equal to, and it's a diagonal matrix. So this A11, we're going to get zeros. Here we get A22. We get entries along the main diagonal. And B is B11. Get zeros there, zeros on down. B22, zeros. BNN. So, with the idea of a subspace for the for vector addition, what we're simply saying is that if you take 2 vectors or 2 matrices within that particular set, when you add them up, is the result of that still of the same form? So here, the question is, if I have 2 matrices that are diagonal, if I add 2 diagonal matrices, is the sum a diagonal matrix? Yes, it is. Now, we're just showing that, which is very trivial. Right? So here, A plus B, get A11 plus B11. A22 plus B22, okay, zeros everywhere else. ANN plus BNN. So indeed, when you add the 2 diagonal matrices, the result is still a diagonal matrix. Secondly, does multiplying a scalar matrix throw off the form of the matrix such that the result is not diagonal? It's still diagonal. So saying some scalar times the matrix A this is equal to KA11 KA sub NN. So here, this set is a subspace of capital M, N, N. Number 5. The set of all n by n matrices A such that the determinant of A is equal to 0. Is that a subspace or not? Let me ask you that question. And do you know what you have to do if you say yes? And do you know what you have to do if you say no? If you say yes, what do you have to do? You have to prove it, show it by rigor. Right? If you say no, what do you have to do? By doing what? What was that, Ali? An example. If you say it's false, you give an example that justifies why it's false. But if it's true, you must show for all, right? That's why the previous example, we said, let A be some n by n, right, diagonal matrix. Let B be some n by n diagonal matrix. We show for all. Number 5, is this true, or would this be a subspace or not? Well, let's see. I say no. And I have one little example to show why it's no. And then we move on. Let A equal to A0, 0, 0, and B equals to 0, 0, 0, 1. Indeed, the determinant of A is 0, and the determinant of B is 0. But A plus B equals to 1, 0, 0, 1, which implies that the determinant of the sum is equal to what? 1, not 0, right? Supposed to be of that form. So what they're saying is that square matrices of the same size, if each of those matrices, the determinant is 0, is that also true of the sum of the matrices? It's not true. That's what they're saying. Yes, sir.
So for all these, basically, what you should take the original statement, plug it into this first two, and if both of them are right, then it's a subspace.
Yes, sir.
Well, it's not.
That's right. Even if one of them fails, it's still not a subspace. Yes, sir. Better, right, than the previous section. You have to show all 10, in the previous section, but here, just show 2. This set is not a subspace of M sub n n. Let me just tell you that this is, yes, this is a subspace. Very easy to show that. There were 2 more, number 7 and 8. Let me go ahead and work through those, and then I want to try to pick up linear combination. Here, which of the following are subspaces of this very big space this space here, capital F, is the space of all functions that or continuous on the interval from negative infinity to positive infinity. A very big space. Very big space that contains a whole lot. So here it says all functions f on this space for which when the function is evaluated at 0, you get 1. And so what they're saying is that, is the sum also the same? No. Let f and g have the requirement that f of 0 is equal to 1 and g of 0 is equal to 1. And let k be any real number. So here what they're saying is f plus g evaluated at 0, is that also equal to 1? Well, you remember in algebra that we said that the sum evaluated at a point is the same as the sum of the two functions evaluated at the same point. Remember, there's a sum, there's a difference, there's the multiplication of two functions evaluated at a point, then there's the ratio, the quotient. You remember those from algebra? It's most important because without them, we can't do anything with algebra. F plus g evaluated at x, this is equal to what? Yes, sir. That's what I'm talking about. A man who we haven't seen in a while, but when he shows up, he's smoking. F of x plus g of x. Yes. Number 2, and 1 and 2 should go together, and I usually put plus or minus sign there. F minus g evaluated at x is f of x minus g of x. 3. This is not the composition of functions. This is called the arithmetic of functions. What's the stipulation for number 4? That's right. Call that the arithmetic, or some books call it the algebra of functions. Why? Because algebra and arithmetic is the same thing. So here this becomes f of 0 plus g of 0. This is 1 plus 1. This is 2. It's not 1. It's supposed to be 1, right? It's supposed to be functions all of that form. The sum has to be of the same result. It is not. Same thing happens with the scalar. And here you get k times 1. We get k, not 1. This set is not a subspace of this monstrosity of a space, one of our biggest spaces in the world. Number 8, Number 8 is what I want to get to. All functions f in the set of all functions that are continuous on the real numbers, for which f of negative x is equal to f of x. My first question to you is this: what set of functions is this talking about? So it's good to know that. That sounds good. Say it again. I heard nothing really. Do you see? It's the set of all even functions. Isn't that the definition for even functions? That f of negative x must be the same as f of x. The odd function is defined as f of negative x is equal to negative times f of x. Right? You get the set of all odd functions. This set defines the set of all even functions. So the question is this simply: if you add two even functions, is the result an even function? If you multiply an even function by a scalar, is that result an even function? Add two even functions, we get an even function. Multiply a scalar times an even function, it's still an even function. Let f and g have the requirement that f of negative x is equal to f of x and g of negative x is equal to g of x. Let k be any real number. Let me just state the two criteria, very general, and sometimes you, to be honest with you, with these two statements, what I'm going to state, you really can't see it. I will put an example down here to kind of just show you where it makes sense. So here, if you have this f of negative x plus g of negative x, and it doesn't matter how it's written. Let me back up. It breaks down into this anyway. Here, f plus g evaluated at negative x. This is f of negative x plus g of negative x, which is f of x plus g of x. And here, if you have k times f of negative x, this is k times f of x. Set of functions of this form is a subspace of this big space. Example, let's say f of x is x squared. Well, isn't f of negative x the same thing as x squared? You call that an even function, or tantamount to saying that the function, the graph, is symmetric with respect to the y-axis. What if there's another function g of x that equals to, let's say 3x squared. So g of negative x is still 3x squared. So if I add the two functions together, f of negative x plus g of negative x, I get x squared plus 3x squared. I get 4x squared. It's still even, right? And then the same thing happens for part B. If you multiply a scalar times the function, does it offset the even nature of the function? It does not. So here, if I say negative 4 times f of x, this is negative 4x squared. It's still symmetric with respect to the y-axis, right? It's still an even function. So that's the idea, behind the question. And it's always good that it doesn't matter what kind of problem that we're given, do we actually understand the problem? Can we see it? And if you can see it, then the write-up is very simple. Definition for linear combination. This is most important. This terminology for linear combination will follow us from now until the end of this semester. We want to talk about does a space or a subset or a subspace, does it span a vector space? In other words, can I take a handful of terms to produce millions of terms that are out there in the space? And so that I do not complicate things in terms of trying to find this and that, and it's a conglomerate of elements. Is it possible to take just a handful of terms that can be controlled, and that this handful represents, it's a random sampling that represents the whole? So instead of talking about the whole, this big vector space, just give me a handful of vectors, and these handful of vectors represents all the vectors out there in that particular space. So we talk about a set of vectors that can span a big space, but then those vectors to span and then to set up a skeleton of all the other vectors. We want to talk about, are these vectors linearly independent? So if they're independent, if they span, both definitions will require an understanding of linear combination. So let's see. Here we say that a vector W, any vector in some vector space, V, is said to be a linear combination of these vectors, V1 all the way to VR, if W can be expressed, we call this, W can be expressed as the linear combination of the given vectors. Now, what's the key about this? That W can be expressed as K1 times V1 plus K2 times V2 plus, and so on, plus K2. Oh, God, I keep dropping this microphone. Yes is the answer to the union of the set, which includes both elements, and that's a good answer. My kids can get away with this, which they did this, and I couldn't argue with them. Did you break this vase or didn't you? And they said yes. No. He said no, and technically he was right, because the union of a statement, when you say did you do this or did you do this, the answer is an element of both. So technically he was right. And so mathematically I couldn't get upset with him. I couldn't whip him. So when my wife got home, she said, did you get that little rascal for breaking this? I said, well, no, because he gave me the right answer. gave me the mathematical answer. He said no to one, but the union is to both. And so, what can I say? Anyway, James, hold it like I'm holding the microphone, I guess. Dang, got it? Anyway, messed up my thought. Okay, so W is expressed as K1, V1 plus, and so on to KR plus times V sub R, where K1 to KR are called coefficients. Now look, these K's, these constants, coefficients, whatever you want to call them, these guys are the key. If I can find such K's that guarantee the linear combination, then this vector here can be expressed as linear combination of the given vectors. So here, number 9, we give a vector. Oh, I'm sorry. Gotta hold it. You know, you see the old ladies at the church, and they're not used to holding the microphone. They go up there, and you give the microphone down here, and they're talking. Mother, hold the microphone up. Oh, okay. I want to tell y'all. Put the microphone up to your mouth, mother. Anyway, here, I want to express this vector as a linear combination of, I'm sorry, my microphone, I like the old lady. Linear combination of U, V, and W. All right. So here, this W here is not reflective of this W up there. Okay. So just letters are. My professor would say letters are dummies and not humans. So if you change a letter, it doesn't get upset with you. Humans would get upset. So let's write it out. So we say that the vector -9, -7, -15 can be expressed as a linear combination of the vectors U, V, and W if there exists scalars. I have 3 vectors, U, V, and W, so I have 3 scalars that correspond to them. Scalars K1, K2, and K3, such that K1 times U plus K2 times V plus K3 times W is equal to this vector here, -9, -7, -15. Now, the neat thing about vectors, my friends, is that they want to, when they're called upon, they want to stand up like men. They don't like to lay down like wimps. They like to stand up. So here, it's K1 times the vector U, which stands up, 2, 1, 4, plus K2 times V, which is 1, -1, 3, plus K sub 3 times W, which is 3, 2, 5, is equal to the vector -9, -7, -15. This, I guess I can write it here. This is the same thing as 2, 1, 4, 1, -1, 3, 3, 2, 5, times K1, K2, K3 is equal to -9, -7, -15. Are you with me? Okay, that's what it means. See if I can just write it out real quick so you can see it. This is actually 2k1 plus k sub 2 plus 3k sub 3 is equal to negative 9. I'm just going here, k1 times that element, k2 times the next element, plus k3 times the next element is equal to this number over here. So this is k1 minus k2 plus 2k3 is equal to negative 7. This is 4k1 plus 3k2 plus 5k3 is equal to negative 15. So we get this system right here. Now on your graphing calculator, because now we can use them, we solve. So what are we putting in our calculator? Two, 1, 4, 1, negative 1, 3, 3, 2, 5, negative 9, negative 7, negative 15. It's what we started out doing in the beginning of the semester. So now we solve that, and when you solve that, you're solving for those constants, k1, k2, k3. If they exist, then we say that that vector negative 9, negative 7, negative 15 is only a combination of the vectors u, v, and w. I get negative 2, 1, and negative 2. Is anybody else? Do you have your graphing calculator? Do you have one? Okay, good. So negative 2, 1, and negative 2. K sub 1 is negative 2. K sub 2 is 1. K sub 3 is negative 2. Now, what are they saying? Here's what they're saying. They're saying negative 2 times that first vector, 2, 1, 4, plus 1 times the second vector, 1, negative 1, 3, minus 2 times the third vector, 3, 2, 5. When you do the string of terms, negative 2 times 2 is negative 4, plus 1 is negative 3, minus 6 is negative 9, and you get them all. So you've expressed this vector, negative 9, negative 7, negative 15, as a linear combination of the three given vectors. Do you see that? Does that make sense? Well, that's good because we use the idea of linear combination to say that vectors span a vector space or vectors span a subspace with the idea of the linear combination. Here, let S be a set of vectors that just does not contain the empty set. There's something in there. So S is a subset, non-empty subset of a vector space V. Then the subspace that is formed of all linear combinations of vectors in S is called the span of S. In other words, is it possible to have a set of vectors that you can produce the other vectors out there in that particular space? If so, then those set of vectors that you have, a small number, we call those vectors a span. They can produce for us other vectors out there. We denote the span of S here as the span of those vectors. And so just a note here that a set spans a space or a subspace if we can write any arbitrary vector in that space as a linear combination of the given vectors. And so number 10, I worked this problem, and then I definitely need to try to get to section 4.3. Determine whether the vectors v1, v2, and v3 span R3. Let me show you the argument to that. And the argument is very generic. The problem can be changed, but the argument is identical. So once you know the argument, then you get it forever. To show that the given vectors, that is v1, v2, and v3 span R3, we need, or we must, show that for any arbitrary vector in R3, for any arbitrary vector, call it B, in R3, we can write as a linear combination of the given vectors. So here, say B is equal to B sub 1, B sub 2, and B sub 3. Because we say that B is an element of R3, so it's a 3-tuple, right, vector. It has 3 things, 3 elements in it. So to say that a set of vectors span a space, then you pick any arbitrary vector in that space, and can you write that vector as a linear combination of these vectors here that you are saying supposedly span that space. In other words, the spanning set or is said to be a set of vectors that the linear combination of such vectors can produce any vector in that big space. So here, that is to say can we find scalars? Now, how many vectors do I have? V1, V2, V3. I need 3 scalars. Can we find scalars K1, K2, and K3 such that, I'm going to write it in mathematics, but the linear combination of those vectors equals B, question mark, because it's the question. That is to say, can we find scalars K1, K2, K3 such that K1 times V1 plus K2 times V2 plus K3 times V3 is equal to B? So here, that is we must show where's V1, V2, and V3? There they V1, V2, and V3. So V1 is, told you vectors stand up, 2, 2, 2. V2 is 0, 0, 3. V3 is 0, 1, 1. Here, B1, B2, and B3. That is, we must show here that this system is consistent. For a system that is consistent, that is, we must show the system is consistent. What does it mean for a system to be consistent? What does that mean? System is consistent, that means that the system has a unique solution, right? Has only one solution. Are you with me? Are you with me? Okay. To show that this system has a unique solution, how would you do that? Well, wouldn't you say that you would need to know something about B1, B2, and B3, right? I mean, there is some arbitrary vector, so I don't know what that vector is. Right? It can be any vector out there in the third space. So, what I'm saying to you is, I can't do anything with that. Because I don't know, just like you, I don't know what B1, B2, and B3 are. So what do we do? Must be. Huh? Set what equal? We just did that. We got that. We just set them equal. We set the linear combination of these vectors equal to B. Because if you did that, you're only showing it for that arbitrary number and not for every vector out there in that big space R3. Okay, let me see if I can bring you in closer. Wasn't it, or do you think that it was a reason why we studied and talked about the monster theorem? Because the monster theorem had several equivalents, right? What's the equivalent statement to a system being consistent? If a system is consistent, that also means what about the system or the matrix or what? Somebody talk to me. It's the monster theorem. You had to write it down on the test. If a system is consistent, then that's tantamount to saying what? It was like 6 or 7 of those guys, right? Just tell me one of them. So you all just memorizing stuff for a test and just forgetting about it and just forget about that in life and just do something else? Yeah, that's what this is saying here. Give me an equivalence to that. We're saying, the question is this guy consistent? I don't know if it's consistent because I don't know what B1, B2, and B3 are. But if this is consistent, then there is an equivalent statement in the monster theorem that says, it said, yes, sir. If the determinant is what now? It's not, thank you. If the determinant is not 0, this crazy problem that I can't work is consistent. Who gives a flip about B1, B2, and B3? I don't care. Just give me the coefficient matrix here, the 2, 0, 0, 2, 0, 1, 2, 3, 1, and just find its determinant. If it's non-zero, that means that's tantamount to saying that this system is consistent, right? Matter of fact, you can pick any statement in the Monst theorem you want to. You can say that the coefficient matrix A can be reduced to the identity matrix. Isn't that one of the equivalents in the Monst theorem? You can also say that A inverse exists. You have your graphing calculator. Just put that in your calculator and just find the inverse. If the inverse exists, you got it. If the determinant is not equal to 0, you can use that. You got it, right? You can put A in your calculator and reduce it. If you get the identity matrix, you got it. So any one of them is fine. We know by the Monst theorem that if the determinant of A is not equal to 0, or if A inverse exists, you can pick any one you want, or if A is reduced to I, then the above system, which is this, AX equal to B, is indeed consistent. It was a reason why we were learning the Monst theorem before. It was a reason. I just wasn't just giving you something. I just want y'all to do this stuff and, okay, see how much you know. No. It's a point. It's a point, man. It's a point. It's a point to my madness. It's a point. It's even a point to what God is doing. Right? It's a point to that. Wow. Bless his name. So look. So what I'm going to do, my space has run out. So what I'm going to do here is find the determinant of 2, 2, 2, 0, 0, 3, 0, 1, 1. I'm going to do cofactor expansion along that second column. So we get 2, 2, 0, 1. We get -6. It's not equal to 0. You got it. So here, by the Monst theorem, AX equal to B is consistent, and thus we say that the vectors V1, V2, and V3 span R3. So here, by the Monst theorem, AX equal to B is consistent, and thus V1, V2, and V3 span R3. So to answer the question whether or not a certain set of vectors span a vector space is actually a proof. And I had one of those problems on the test. And it's that argument is the argument for every last one. Okay. Let me stop there with this section. I got 15 minutes to cover a big chunk of 4.3. Let's take a 3-minute break, and then we'll come back and I'll try to give an introduction to 4.3.